Okay, this screencast is on colligative properties. And the thing to note about colligative properties is that changes in colligative properties depend only on the number of solute particles present, not on the identity of the solute particles. Okay, so it really is just the number of particles. So we'll be talking about Avogadro's number and moles to represent the number of particles present. The colligative properties that we'll be looking at is vapor pressure lowering, boiling point elevation, melting point depression, and a limited look at the osmotic pressure and how the number of particles in the solution affect those four properties. Remember vapor pressure. Because of these, if you have just the solid alone and a closed system represented by the watch glass over the beaker, remember that at a given temperature, the rate of particles going into the vapor phase is going to be equal to the rate at which those particles are going back into the liquid phase, and that is for a solvent alone. When I have a solvent and a solute, a solution, okay, these solute particles hinder the amount of particles that can go into the vapor phase. You will still set up an equilibrium of the rate at which particles go into the gas phase is going to be equal to the rate at which they come back into the solution or the liquid phase. Okay, but it is going to be less of a vapor pressure, a lower vapor pressure, because these solute particles prevent those solvent particles from escaping into the vapor phase. So the vapor pressure of a solution is going to be lower than that of a pure solvent. And we can calculate what the vapor pressure is going to be of the solvent, okay, by Raoult's law. The vapor pressure of the solvent, okay, of a solution is going to be equal to the mole fraction of the solvent multiplied by the vapor pressure that would exist if it were a pure solvent. Okay. As mentioned earlier, when we talked about the mole ratio, or the mole fraction, I should say mole fraction, not mole ratio, mole fraction, here is going to be the mole fraction of the solvent. Okay. So how does Dalton's law of partial pressures relate to Raoult's law? Interesting question. Let me know your thoughts. Okay, let's take a moment and look at this boiling point elevation and freezing point depression. Okay, so non-volatile solute-solvent interactions cause the solutions to have a higher boiling point. And remember, the definition of boiling point is the vapor pressure, when the vapor pressure of a substance is equal to the atmospheric pressure. If the solution has a lower vapor pressure, then it's going to take a higher temperature for that vapor pressure to be equal to the atmospheric pressure. So you will see a higher boiling point for a solution than you will have for a pure substance. That is part of the reason why you put salt in water. It's actually so it boils at a higher temperature and cooks things faster because you're cooking it at a higher temperature. Okay, for the same kind of reasons, that your vapor pressure of a solution is going to be higher than a vapor pressure of, boiling point is going to be higher for a solution than for a pure solvent, would also cause the freezing point to lower. It's one of the reasons why you put salt on ice in your sidewalks in the winter, is so that you lower that freezing point so it stays a liquid at a lower temperature. Okay. Can we calculate what the change in boiling point would be? Yes. Remember, this is a delta, so the change in the boiling point is going to be equal to K times the molality of the solution. K is the molal boiling point elevation constant, and that is a property of the solvent. So you need to have a table, something like this, in order to apply this equation. Remember, molality is the moles of solute per kilogram of solvent. Okay. So once you calculate delta T, to find the actual boiling point, you have to add that to the normal boiling point of the solvent because you're making a change, you're increasing that boiling point. The title here is a little wrong. Let's fix the title. This is freezing point. Depression. Okay. The change in freezing point, again, a change in the temperature can be found by, again, using the molal freezing point depression constant of the solvent, again, given in a temperature, or in a table, times the molality of the solution. Okay. And then to find what the new freezing point is of the solution, you would then subtract that from the normal freezing point. Oh dear, who made this slide? Normal freezing point of the solution. So notice that both of these delta T's doesn't depend on what the solute is at all, just on how many particles are present. Remember that molality is moles of solute over the kilograms of solvent. Now, there is something to remember. The colligative properties depend on the number of the particles dissolved. But if you remember, if I dissolve a ionic compound, I might get more than one particle for every mole of compound that I dissolve. So if I had a 1 molar solution of sodium chloride, you're really looking at 2 moles of particles that would be in the solution. Okay, hopefully you know that, right? This is going to form 2 moles of particles. So you would theoretically use that, the 2, to figure out the molality. Now, all solutions are not perfect, right? And experimentally, we'll see that a 1 molar solution of sodium chloride does not show twice the change that a 1 molar solution of methanol does. So we have to account for some non-ideal behaviors. And that's known as the Hoff factors. And 1 mole of sodium chloride in water does not really give rise to 2 moles of ions. Some of that sodium ion and chloride ion kind of reassociate for a short period of time, because remember, these are ions. So they do get attracted to each other and don't really act as 2 separate ions. So the true concentration of the particles is somewhat less than that 2 times the concentration of the sodium chloride. And remember, reassociation. The more ions I have in solution, the more likely they're to collide with each other, the more likely that they're going to behave non-ideally. So the Van Hoff factors depends on the concentration of your solution. Okay? So for sodium chloride, for a fairly concentrated solution, it would be a 1.7 is the Van Hoff factor, all the way up to an ideal very dilute solution that would have that ideal 2 moles of ions for every 1 mole of sodium chloride in solution. How do we use this Van Hoff factor? Well, we just add kind of a fudge factor, okay, this Van Hoff factor, into the earlier equations that we use for change in freezing point and change in boiling point. We're going to stop the discussion there and not go on to osmosis.